So our second exam's a week from today. Make sure you're getting your homework and quiz done. The quiz is for Chapter 8 and 9. We have two sections from Chapter 9. So they're fairly short sections. We might be able to get to through 9.3 today, but we'll just have to see how it goes. Yeah, and then the exam 2 review that's not graded is underneath the quiz for Chapter 8 and 9. Just additional practice problems if you need it. Okay. Were there any questions on the homework?
Yeah,
Yeah.
I've got one. I'm struggling with 8.4, number 9. I have the question. If you just want to like look
Okay.
for it or something.
Let me. Homework 8.4, number 9.
Yeah.
Okay.
So it's the integral of x squared divided by the square root of 16 plus x squared.
The square root of 16
Plus
plus
x
x squared.
Yeah.
Okay.
Yeah, and then the like the show me how they use the reduction formula and they get like a 1/2 out of part of it, but I didn't do that. I did it by parts.
Okay.
For some reason I'm not getting this 1/2. So my
All right.
answer is just off slightly, and I'm like,
Okay.
why?
Well, all right. We might have to show us what you did when you did it. Okay. So we'll factor out the stuff in the radical. We're going to factor out the 16 so that we have 1 plus x over 4 squared, square root of all that, and the 1 over 4 out here. So what substitution are we using here for 1 plus x over 4 squared? Tangent. 1 plus tangent squared. So x over 4 is tangent. That means, well, I guess we'll look at it this way. X is equal to 4 tangent. And dx is 4 secant squared. All right. So then this here means that x squared is 16 tangent squared theta. So we have this 1/4. We have our 16 tan theta squared over the square root of 1 plus tangent squared.
Times 4 secants.
Yeah, times, yeah, sorry, I put the theta, d theta in the wrong spot. Times our dx, which is 4 secant squared theta d theta. Okay. Yeah. Is everybody okay with that? Maybe not if you haven't done the homework, but hopefully you've done some of it. All right, so then we simplify here. This thing, secant square root of secant squared, so all of that is just secant. So we have one of those canceling with this one. So it's 16 over 4, we'll just call that 4. Well, rather, we'll call that 16 and divide the 4s. So we have 16 tangent squared secant. d theta. Is that right?
Yeah.
Okay.
How do you pull the 4 out and then you pull the 16 out?
Yeah, well, I just canceled these two and then left the 16.
But if you pull the 4 out, don't you pull it out of the 16?
No.
No.
Not from this one up top, no, because that came just from the straight substitution, not from the original integrand. Okay, so how do we integrate tangent squared secant?
So the tangent squared can turn into, is it secant squared minus 1?
Okay, so if we write tangent squared as secant squared minus 1, this one, oops, does that help us? Theta? Yeah.
If that's the case, how did that secant cancel out? That's supposed to be square root of secant.
It's square root of secant squared, right? So 1 plus
Oh,
tangent, yeah, and it
okay.
turns into a secant. Yeah, so we took the square root of everything.
You just, you'd already canceled out that.
Yeah. So could we do that? Would that be helpful if we wrote tangent like that? Because then we would actually be integrating secant cubed minus secant. So we did secant cubed in class where we split it up, integrate by parts. And then it's one of those integration by parts problems where you end up with the integral on the same side and you end up having to solve for that integral. Is there a method for powers of secants and tangents that we got from 8.3?
Use substitution.
Yeah, so could we, that's another option here. Could we use substitute here? Let's just kind of keep that in the back of our heads. So it probably wouldn't work here for this one, right? Because normally I think that algorithm was if there's an odd power of secant, then we would split off a secant tangent. Right, so like even if we thought about it that way, if we split off a secant tangent, put it with our differential, then we just have this tangent here. Right, so under those circumstances, we would say split off a secant tangent, let u equal to secant theta, right? And then the remaining power of tangent that shows up, you use the Pythagorean identity. So that's not going to be helpful here because at the bare minimum with those we had a tangent squared left, so we could say tangent squared was secant squared minus 1 and write that in terms of u. So that doesn't look promising. But worthwhile remembering those for sure. Okay. So we've addressed 2 of those things. One of them is more promising than the other. Any other ideas? Well, yeah, because then you would be integrating like with quotients and stuff. So I don't know that I would want to do that. You have sine over cosine squared. I mean, we could look at it and see if, it might work out. So if we wrote that as sine squared over cosine squared, and I don't know, maybe you want to leave secant, maybe you want to write it as 1 over cosine. So then that would give us sine cosine theta. Sorry, sine squared cosine cubed on the bottom if we moved it up. So That's equivalent to what we have. Is this easier to integrate? Well, the ones we saw in A3, we saw some that were similar to that, but we saw something to the effect of, like, it was like cosine maybe to the -3 times sine cubed or something to that effect. So in that instance, we would just split off one sine. Remember doing that? Split off a sine, and then that's U substitution. But we've got cosine that's odd, but it's a negative odd power. So would that reasoning with sines and cosines still work here? Maybe? Don't know. Okay, so here's our suggestion. We at least know we can tackle this. Yeah, 16. All right, and that's going to give us this. And so hopefully you can do the antiderivative of secant, if we remember that one. Again, secant cube's a little bit more involved, so that's where they're saying use the reduction formula to do that.
Yeah.
Yeah.
And they're getting like a 1/2 comes out from the reduction formula. That like when I did the way that we did it by parts, that 1/2's not coming out. So I'm just off by just half.
Oh, so okay, I see what you mean. All right. So let's look at it. Let's break this up and look at this one. What's the integral of or antiderivative or whatever 16 secant theta?
16 natural log of secant plus tangent.
Right. Remember that's ln absolute secant plus tangent. All right. So, I mean, we could go through this process of integrating secant cubed. Remember I said you don't need to remember those reduction formulas. So we did this prior in 8.2, I believe. So, instead of going through that again, it's kind of time consuming. Let's just look at our results that we got previous to. Wherever that was. Maybe that was an 8.4. Sorry to mislead you. No? I know we did it. I can't remember when we did that. Which one?
8.3.
Okay.
Yeah.
I didn't look hard enough. Oh, there it is. Wait. No. Number whatever this one is.
23.
Number 23. So we had 12 secant cubed, and we said here, oops, at this point we would just do secant cubed and then multiply everything by 12. So here's our result, integration by parts, and then we ended up with secant over here on this side, or sorry, secant cubed rather. So we just added that to this side to get 2 of those, and then we solved. So that's where the 1/2 comes from. is the fact that you have two of these.
So wouldn't I technically have two natural logs of secant and tangent?
Right, you'd have two of those, secant, tangent, and natural log. I'm gonna put this in here. So it was 1/2 secant theta, tangent theta, plus this. That one. So that's, we'll stick here that this is all of this. Okay. And we have minus 16 Ln. Some constant. So we have 8 of those and a minus 16 of those. So yeah, 8 of these minus 16 of these. Yeah. Plus. So does that help? I don't know what they're showing, but.
It did. I found where I'm goofing up.
Okay. Okay. So then also remember, you know, a question like this probably not on the exam, just because it's secant cubed. They say use the reduction. X over 4 is tangent theta. So that's where we'll go from here. So I think maybe from here we can fill in the rest. I don't know, 16 plus x squared, whatever. So all we have to do is just resubstitute. So hopefully you have it from there. Okay, were there any questions on what we did? I guess if you haven't got to that, then yeah, the homework helped us say use reduction formula for the secant cubed integral. Excuse me, were there any other homework questions? Alrighty then. So here's the example we left off with, negative infinity to negative 1 of 1 over x squared. We saw that converges. So just giving you a glimpse of where we're going, just so we can have some context here. You know, outside of finding like volumes, areas, you know, stuff like that from integrals, really the bulk of this class is how we represent functions by, how should I say, how can we represent a function as a polynomial, for instance? So many functions like sine and cosine, natural log, e to the x, those kinds of functions have a polynomial representation. And to say this function like sine of x is equal to this infinite polynomial, we have to, through there somehow, we have to be able to determine, does this particular polynomial actually converge on the sine function? In other words, if we can show that a polynomial converges and it's sine x, then what we show is sine x is equivalent to this infinite polynomial. So the idea of convergence in later sections or chapters is really what allows us to equate. So if we say something is convergent, then we can say that this thing is equal to this thing because this polynomial converges to sine of x or something to that effect. It involves a little bit more of development than that, but the idea of convergence here is just saying that we have a finite area. Divergence means we have an infinite area. But the terms convergence and divergence will be a huge part of chapter 10 and 11. So here in blue was the 1 over x function that we had prior to. And we worked that example and said that the area from 1 to infinity was infinite, it diverged. But the graph in red, 1 over x squared, that converges from 1 to infinity. And so we sort of alluded to why that might be the case. And it kind of has to do with how fast things are decreasing. So even here at 5, you have a significantly less, it's less than half of what you would have below the curve for 1 over x. So I think for now, that's probably really the only context we have to think about why that would be the case. It just has to do with the nature of, how fast is it decreasing, really? How fast is that function decreasing? So anyway, like for me, looking at something like that, it's, it just really begs further investigation, right? Like, why does this thing have an infinite area, but the thing in red doesn't? Even though they're both going out towards infinity. So I don't know, it's weird, right? I think it's weird. All right, so another example here, improper integral from 2 to infinity functions x over x plus 2 squared. So the issue here with this integral is the infinity. So we just want to say that's the integral from 2 to b or t or whatever you're using, and then calculate the limit as b approaches infinity. Okay, so what method of integration would we use to find the antiderivative?
Can we do by parts?
By parts,
Trigonometric.
yeah, I think by parts would work.
Trig.
Trig, it's not, a trig substitution might be applicable if we had x squared plus 2. But since we have on the bottom x squared plus 4x plus 4, so you could try integration by parts, or partial fractions could work here, right? You got a polynomial over a polynomial. Polynomial here is factored for us already. So we've got a repeated linear factor for partial fractions. So you could try those. I think it's easier for a u substitution. I mean, I think by parts and partial fractions would certainly work. But let's let u equal x plus 2. du is dx. And from here we know that u minus 2 is x. So I think we'll just work for the antiderivative at this point and then come back with the limits, or the limit and the bounds. So what we have here is x, which is u minus 2 over u squared times dx, which is du. So hopefully we've seen enough of these types of problems that we know what to do from this point. What are we going to do from here?
Split.
We're going to split that up, right? We've got u over u squared and minus 2 over u squared. Well, we'll just go ahead and simplify this. So u over u squared gives us 1 over u du. Then we have minus 2 u to the negative 2. So antiderivative of 1 over u, or u to the negative 1, is what? Right, ln, make sure ln, absolute value of u. Just until you know that, where that thing's at, right? If it's always positive, we don't need absolute value. And then we have u to the negative 1 over negative 1. And then we'll resubstitute u as x plus 2. Or, I don't know, just depends on how you like to write these things.
How's it become ln of u and not ln of u squared?
Because it's just the antiderivative of 1 over u when we split up u over u squared.
Wait, but when you split it into u over u squared, then minus 2, oh, and then the u squared, okay.
All right, so then the original integral, the limit as b approaches infinity, 0 2 to b of x over x plus 2 squared is equal to the limit as b approaches infinity. Now we have our antiderivative. Evaluated from 2 to b, rather. Remember, the limit here is the last thing you're going to do. So evaluate according to the fundamental theorem. So we have the natural log of b plus 2 plus 2 over b plus 2. There's upper limit minus lower limit, ln of 4 minus 2 over 4 Hmm. Oh yeah, plus that. Yeah. Okay. So then we apply the limit as b approaches infinity. First two terms. What's the limit as b approaches infinity for ln of b plus 2? Ln of infinity, right? That's infinity. So this is approaches infinity. So really you don't need to do anything else, right? As b approaches infinity, 2 over b plus 2 approaches 0. So this approaches 0. This is a finite number over here. So you've got infinity plus 0 minus some number, still infinity. So we have another divergent integral or infinite area.
Did we just get E7?
Do what?
Did we skip E7?
I don't know, did we?
Oh, you don't have it.
Oh. Yeah, 7 is hidden somewhere in that packet. You have to find it. No, I'm just kidding. I guess I forgot number 7.
It's not those.
All right, from 2 to infinity. So an infinite area. And you know, I guess we could sort of compare this to the last example, 1 over x squared, where we saw that converged. This is x over essentially an x squared, right, as we get towards infinity, which is essentially a 1 over x type scenario. So that's infinite area. Okay, anybody have any questions on that? All right, so I'll let y'all evaluate this. What's the issue here with this integral, though? Yeah, how come it's not proper? Right, because 0 is fine in this function, right? The function is defined on 0. However, the function's x cubed over x to the 4th minus 1 is not defined when x equals 1. So this is, you know, similar to what we've done, but it's our first instance of, instead of approaching infinity, we're approaching a finite number. So give that a shot. Yeah. Did you print out?
Yeah.
Did number 7 print out?
On
Yeah, that's
page
so weird.
4.
Yeah. I mean, maybe we can come back to that. But it wasn't there in this for whatever reason. I didn't see it anyways.
It got hidden by that graph you put in.
Maybe. Oh, that's so stupid. I'm an idiot. I swear I didn't see that. Yeah, we can come back to that. Well, not technically non-infinity.
Right, I don't get that.
Did I get to this?
Yeah.
Wondering, like, why, like, sometimes it could be. Or like how to like get to that number,
Like when did we learn how that happens?
how you get to like n equals 4 to 1.
Oh.
Is that
As far as the integral goes?
It equals that, yeah. Well, just that's confusing, you know, like, that equals a number, like how do you actually use that?
Have we had one that's been equal to a number yet? Yeah, that 1 over x squared was equal to 1. Yeah. So how do we justify that?
Yeah.
It really just depends on the function of where you're looking from where to where. And then that comes out in the work. So that's our justification.
In the integral, it just like,
Yeah, right, the 1 over x squared became, this thing plugged in to the limit, we got a finite number. You know, because just even on that first page, like, some limits are, even though initially they look like they're infinite, they're still finite, like this. Something like that. Right? That's still a finite limit. So stuff like this that comes out that we compute the limit of, that depends on the antiderivative, which depends on the function you start with.
Even if you like,
I don't know if that answers your question, but it sort of comes out, like we'll see whether it does or not.
Even if you keep adding on numbers, those numbers won't affect the being. Like if you have one, which just makes something. Seven adds up. Or 0.0.
Right.
Yeah, zero's the second. I don't know about zero.
well, because it approaches 1. Yeah.
Yeah, it's still basically one.
No, it approaches zero. I don't know what So that was
Yeah.
Yeah, right. And so that tells you that. That tells you what this is.
negative area.
Right.
Volume.
Yeah, that function is below 3x. With an infinite area. Yeah. Cool.
Well, you know that because you read
because I didn't use that.
I believe you. I'm thinking about cycles.
Oh, what's the circle?
Just so like how we made it into new set functions.
you have to like like it seems like it's 0, but it's really 0. We don't know why.
Yeah, so like some things converge, some things diverge. But some goes like a sine. It goes up and down, up and down. If it's like decreasing or something, we consider it to converge conditionally. So like based on how many sines you get it equal.
I'm trying to catch you as
This thing. I don't think it's in extra units, but
So that would
there was like a where it's just like a ton of rules on what diverges.
he said that that'll be like
Oh, yeah. It's like zero use.
like I just introduced you.
It's just like, it's like
Like your basic rule of
x plus 1 equals 1. Take the derivative. 1 plus dy equals 0.
Because y is the same as y.
Or negative 1.
Yeah. As upper limit gets closer to 1.
If you take the derivative.
But the natural law, as y gets closer to 1, function gets
And then you go like, the ladder is moving up, and this side is changing.
Yes,
That's right.
So that's approaching negative. That's approaching. Oh, yeah. So.
I've never taken this many
Oh, shit.
Also, it didn't fit this one, but it could have.
So then
The only one is where it's taking notes, it's not like so well.
Wait, so it does not appropriate?
Yeah, so it's not that like this basket. Oh, no, they do it well. So like, I like how they do it, and I don't work on that, but I was like, I
Guided solution.
Yeah,
Not at all the way that would.
but it's still better than like,
I just realized
get it
that
back in time, you don't like.
he started it's like, oh no.
Yeah, that's my
Exposed.
I think my math lab is like,
Yeah, once you're there, I guess I realized that
Like,
this
the last
is where
exam,
it's
Like I might try to do myself where it's like, like I just solve partially like this. It's nice that you actually go back, because like my physics, I'm taking it online, but it doesn't tell me if I got it right. Well, it tells me if I got it right or wrong, but not what the right answer was. It's just like,
I felt very should be doing like that, but it's like.
oh, that's the thing is that I guess we're kind of spoiled with our work with my math lab because I'm so used to just being like, I want 100% of it as long as I have time to which actually makes me figure out how to do it.
Yeah.
So like with physics and stuff, I'm like, I don't know if I got it right or wrong, and I'm not going to do it until I turn it in, and now I'm not going to do it again.
You're not like, it's not like you're gonna know how to get the right answer.
Yeah.
It's just like permanently wrong.
It's just wrong. Like with my math lab, like actually focuses on
Yeah, or if it's like, you don't get to like we will.
yeah.
I can't believe you did. Because natural law is
Put it out with your hands.
So you tell them you be a teacher.
Wait, did it say two?
See those numbers when Thanks to did you look at the next like homework assignments too? There's
Yeah.
anything on the homework assignments.
It
It's
seems
like,
like it's early semester, so it's just.
yeah, you should look like it's for
Yeah.
2019.
The class goes off of
Everyone's just like, there's a reason.
Really? Everyone puts it like,
You don't have a background in computer programs. I don't have that. I go along learning that whole class on side. For half homework. Actually.
He said, we can do it in Excel. I'm like, you can't do it in Excel.
You don't even know what that is.
yeah.
Do you have
No, we have to like, program like these algorithms to do projectile motion. We get like half of homework assignments during the semester.
Yeah, it's not even worth
And he was even like the whole time he's trying to
again, why would I do it?
Yeah, that sounds important.
I don't even have any like.
Yeah,
So I'd have to like learn those things, download those programs. And then, like,
all you gotta do is take another class.
You think I have?
In order to get the whole 5%, like, is that maximum? You're gonna give me the actual capital compensation. And like my computer programming.
Like, I hate those programs. This is like your life is this class. No, it's not. I think like
Like my life is not even just maybe just maybe
he does that every year. He just works out of this. He also teaches physics. So I do rotates like who gets what class. I think because he probably got. And that's what he should. So. You'll read the textbook. I do like the papers, like in my house, like really learn like how to do problems. Because you like just go by tangent. And it's just like anybody can help you get this problem. Sometimes it's like you can get through like 7 degrees. I have the time, so it's like.
Because our teacher was like, yeah, so they should take an advanced calculus. So, I have no idea.
Once a year, but it just gets through Gen 10 1.
It's 111 basically.
Yeah, it's just 111, which is actually really easy at the college level. Like if you took the class year D,
It'd be so much easier than AP.
the AP test is
Our
much
AP
harder than our
class,
final.
like the advanced chem class, did like, they've done in the last like 6 days, did it moves like as fast as this class. What it's just like the actual college class.
That's the thing is actually, when you sign up for classes, there's like a little compared to AP.
And then you get guaranteed credit. You get a grade note, you get one
This one is like.
I got like a 97%.
Yeah, that's like.
So, like, I remember, like, I never did read stuff. I remember people like, I read out all the names. Yeah, just really fast.
I like Ireland, and Ireland was like a fun class. Yeah.
No pressure. Gen Chem 2 is pretty similar so far. It's not like
The hardest part for me was like memorizing geometry.
Yeah, I'm worried about like the you don't do any of that in Chem 2. I think all right, but my last one's gonna be like all of that.
Yeah,
And they're like it's like based on statistics too. Like we're not doing overtime like nothing. It's just it's like
That's the thing with physics though, is like I feel like we're also the statistics side.
yeah, it's a
With the Taylor book. And it's interesting, like I've never taken any statistics in my life.
Either you substitution.
I think it's high school and it was actually like pretty close like that. I think it was physics and all of that actually like you'll see probably participation.
Like, it would have been easy if I took it like after classes, but our high school didn't have really no calculus. Like, some teachers like is really good at calculus.
If you really know calculus, you teach those.
Yeah,
That's like
they get to like this and they're just like, stuff happens.
like it came up.
From there you solve.
Yeah, and that's how our physics teacher was in high school. She was like notoriously like never did physics class in college. She just got stuck in the physics class. She was like, actually like here's the answer.
My physics teacher, I don't know why she left this year. I don't know why she was there, like for how long she was. She had like 2 doctorates. And I was like, what do you do? Close. Like teaching in high school. And like my engineering teacher in college.
Can't think of any high school that I know that. Mine certainly wouldn't.
Yeah, all in physics are so
Are you?
No.
Oh, no.
Well, it's actually Illinois 1. Right. And as your almost SB, this is one line.
Yeah, no,
You couldn't teach it.
Well, no, the L, no, the L and the zeros on the
The
top.
thing is like AP physics doesn't really count. So what it
But
got
as
you
the argument is
Like,
supposed to
like I'm taking it's not
Yeah, I'm gonna
Yeah. So that's going to turn into a negative.
So when I go to college, I have to take physics one. Like when I go to college, everyone's gonna think I'm a genius first. Because I've already taken all just school. But then second year, we'll be like, what happens? I'll be like, I've been taking this class every time. So do it. Because I'm probably gonna take calculus again. My third year. I'm just
You know how like in an algebra, like they kind of go over one thing, and there's like
So really, when you're looking at these limits, please be aware of what direction you're approaching from. This function is defined on, or we're asking what's the area from 0 to 1.
dude, blank.
So you can't approach 1 from the right. You have to approach 1 from the left. And then this function is in log form once or what's in log form, but if we had a 4 up here and a 1/4 here, that's in logarithmic form. We've got 1/4 natural log absolute value of x to the 4th minus 1. So if it were x to the 4th plus 1, we could drop the absolute value, but it's x to the 4th minus 1. Sometimes it's positive, sometimes it's negative. And we calculate the limit as b approaches 1 from the left, antiderivative from 0 to b. So we'll do this first. All right. So then our second term is just 0. ln of 1 is 0. Now in the sense of b approaching 1 from the left, that's numbers that are slightly smaller than 1, and we're raising those to the 4th power. So numbers that are slightly smaller than 1 raised to the 4th power, then subtracted from 1, are those going to be positive or negative? Those are small negative numbers, right? So b to the 4th minus 1, this is still the ln of a small negative number. So we still have the absolute value around that, so we don't have to worry about that. So we've got 1/4, the natural log of a small negative number. If you remember the graph, or if you just remember the sort of the end behavior of the natural logarithm, approaches negative infinity. So I mean that's basically like we're just looking at something that's like this. What's the ln of 0? In the sense of just evaluating that function, you can't do that, right? But we've got to take it in context. It's the context of a limit. Arguments approaching 0, the function approaches negative infinity.
You were saying, like, about the direction.
Yes.
So how's that from here?
Well, so all right, because we're not actually computing the limit on the logarithm itself, right? If we're going to look at that, we have to look at it as we're computing the limit on the log of the absolute value of x to the 4th, essentially, since it doesn't like b's and such, minus 1. So if we're saying that we're approaching this function, if x is approaching 1 from the left on this function here, then we're approaching, well, that's not 1. Where's 1? Oh.
Somewhere down there.
All right. So this is 1 here, this goofy spot that we can't.
It's negative 35.
Yeah. Anyhow, we have to look at this function. Technology has failed us once again. So if we're approaching 1 from the left, I don't know what's happening here, but we're approaching 1 from the left on this function. It's hard to tell. This thing probably is going back up right here. So anyways, these are small negative numbers. But if we just went ahead and plugged that one in, right, if we went ahead and plugged that one in, we say it's just a small negative number, I mean, it's virtually zero. So we might as well look at this graph and say, I know that this argument is approaching zero on the natural log function. So then I don't have to worry about the argument as another function in and of itself. Yeah.
But you're just saying like the direction matters. So if it doesn't, have a limit on both sides,
If it only has a limit on
like
one
you might
side.
get the wrong, like if it's an asymptote like this,
Mm-hmm.
so
Right.
it might be positive or negative.
Yeah.
So you're just saying pretty much make sure you're looking at the right.
Yeah, the direction's important. We saw in this particular instance, because we had the absolute value, that it really didn't matter that much,
Yeah.
right? Whether we approach one from the left or the right, taking the absolute value, it's still going to be a very small positive number that you're looking at the ln of, right? But in a lot of instances, the direction from which you approach matters. And we, like, just like you mentioned, you know, a function that looks like this, you know, a function that looks something like that, it totally matters what direction we approach, because whether you had infinity here or negative infinity here, you still come up with the notion that this is a divergent integral, right? But it's a little more specific than that, because this negative infinity tells us what about the divergence or the infinite area. It's negative, which means it's below the x-axis, right? So, I mean, you can get a little bit of information out of that. But in general, the direction matters.
That's the spirit.
Sorry. I'm just trying to get closer. Anyhow, that's the function. We know that's an infinite area. Below the x-axis. So that area is infinite. All right, well, since we found number 7, let's go back to number 7. Yeah. Yeah, zero's over here. So that, then as we approach 0, that function was approaching its horizontal asymptote. Okay, so number 7, 0 to infinity for this integral. How are we going to find the antiderivative here? Arctangent. It's a lot more efficient if you know that that's arctangent. Otherwise, we do what? What could we do there? Yeah, trig sub. So upper limit again, approaching infinity. From 0 to b. Okay, we said that was the arctangent. Specifically, what is the antiderivative then?
over 7 times arctangent of x over 7.
Right, 1/7 inverse tangent of x over 7 from 0 to b.
This is approaching infinity from the right.
All right, so plugging in our bounds, we've got the limit. And I'll just put the 1/7 out here this time. Inverse tangent, b over 7, minus inverse tangent of 0. So what's the inverse tangent of 0? The tangent of what is 0? 0. So that's 0. What's the limit as b approaches infinity on inverse tangent of b over 7? So that's essentially the same question. On the graph of inverse tangent of b as b approaches, or think about it as x approaches infinity on the graph of inverse tangent. What does inverse tangent approach? It doesn't oscillate. Yeah, what is 1.57?
Feels right.
Pi over 2, yeah, pi over 2.
Yeah, because sine gets really big and cosine gets really small.
Sorry, that's kind of straight there. This is your inverse tangent graph. Inverse tangent had two horizontal asymptotes. There and there, both at, well, pi over 2 and negative pi over 2. So yet again, we're approaching infinity, but the function that resulted from the antiderivative doesn't approach infinity as its argument approaches infinity. Inverse tangent approaches pi over 2. So our integral converges. To pi over 14. It's definitely worth remembering that about the inverse tangent. So I mean, just depending on the scale, it is sort of like this. If you just looked at it 1 to 1, it almost looks flat. So we'll exaggerate the scale here, just as we go out towards infinity. We have a finite area there.
That's part of, no, it's at .02. Divided by 295 times the standard temperature, which is 273.
All right. You have any questions on that? All right, let's take a break. All right, let's take a look at, we've got this example and one more. So for these, you should be familiar with all the methods we mentioned at the first of the section, which included L'Hopital's rule. Those definitely are viable outcomes when computing these types of limits. So again, our integrand is not defined when x equals 6. So we're going to compute the limit as b approaches 6 from what direction? From the left. And what is the antiderivative of this function? Inverse sine. Yeah, inverse sine of x over 6. Remember the inverse sine and cosine were the only ones that didn't have that multiplier of 1 over a in front of them. So we have inverse sine. Trig substitution works as well, as we saw in 8.4. So inverse sine of x over 6 evaluated from 0 to b.
Wait, why?
Huh? All right, so inverse sine of b over 6 minus inverse sine of 0. So what is inverse sine of 0? 0, because the sine of 0 is 0. The inverse trig functions output what?
Values.
Yeah, what kind of values?
X values, angles.
Angles, right? So when you have to answer a question about inverse trig functions, you could put it in on your calculator, but you could also ask the question, the sine of what angle outputs 0, right? So just a reminder. And as b approaches 6, I don't know what that is. As b approaches 6 from the left, what does inverse sine approach? Yeah. So that's approaching the inverse sine of 1, right? I don't know why I keep writing that. But the inverse sine of 1, the sine of what angle is 1? Pi over 2, so inverse sine of 1 is pi over 2. Again, we get another finite integral, or another finite area. Oh yeah, probably. It's getting inverse and the negative mixed up here. Yeah. Okay. So finite area for that one as well. And again, in the sense of this function, if we were to look at it, you're approaching, on one end, you're approaching its vertical asymptote. Questions on that? All right. So last one. So the function x ln of x is not defined when x is equal to 0. So we're going to have to compute the limit a to 1 over 10. The limit as a approaches 0 from the right, 0 from the right, of x ln 10x. How are we going to evaluate the antiderivative? By parts. Yeah, so it's just the product of two functions of x. It's integration by parts. So we're going to let u equal to which one? ln, right. So remember the other, on the converse of that, let u equal ln, we have to think about dv being the largest part of that integrand that we know how to compute the integral or the antiderivative. Okay, so u and dv, that makes du 1 over 10x times 10. So 1 over x dx is that derivative. And then the antiderivative of dv to get v. So the antiderivative of x is x squared over 2. So we'll just kind of do this for the side work here. Then the antiderivative of x ln 10x is equal to u times v. Minus the integral of v du. So we have minus the integral of x over 2. So we've got x squared over 2 ln 10x minus 1/4 x squared. Okay, any questions on that? Review of integration by parts. Then we have our antiderivative. Go ahead and plug this in for limit as a approaches 0 from the right. Well, I guess, yeah, I'll go ahead and write it here. From a to 1 over 10. 10x dx equals to minus 1/4 x squared. Evaluated from a to 110. Okay, so plug in our bounds, then compute the limit. So we have 1 over 10 squared. 1 over 10 squared divided by 2 times the natural log of 1, which is 0. minus 1/4, sorry, that's 1/1/4 x squared. I don't know what happened to the square. 1/10 into x squared, 1/100 times negative 1/4 is negative 1/400 minus the function evaluated at a. So a squared over 2 ln of 10a minus 1/4 a squared. All right. Any questions on where we're at? So the limit operates on the last two terms. So we have our negative 1/400 here. We have minus the limit as a approaches 0 from the right, a squared over 2 ln 10a, plus the limit a approaches 0 from the right, 1/4 a squared. So this one's pretty trivial. That's approaching 0. What is a squared over 2 ln 10a approach? Infinity over infinity? Yeah, but in a specific way, right? Initially it's 0, so here direct substitution. It's 0 times, yeah, negative infinity, which is the indeterminate product that is not directly applicable to L'Hopital's rule, but it is related to L'Hopital's rule. So let's do this over down here. Since that is an indeterminate product, remember L'Hopital's rule was applicable to 0 over 0 or infinity over infinity. So that's, both of those are quotients. You've got a product. How do you turn a product into a quotient? So if we have any hope of applying L'Hopital's to this, it has to be a quotient. So how would I turn this product? How would I write that equivalently as involving a quotient? 2 times a third. Well, right, I mean, 2 times a third is a different...
I mean 2 divided.
2 divided by 1/3? 2 divided by 1/3. Right, so that's an equivalent representation of 2 times 3. And this is, we turn this product into a quotient. So that's what we have to do with the a squared and the ln 10a. We have to say that algebraically this is the same as the limit as a approaches 0 from the right of ln 10a over the reciprocal. So what I'm going to do just to simplify this a little bit is I'm just going to take that half out. You can keep the half in if you want. The same result will emerge. Okay, so now it's a quotient. Now, what happens when we evaluate the limit as we approach 0 from the right? What do we get? Yeah, ln is approaching what as its argument approaches 0 from the right? Negative infinity. And 1 over a squared approaches what? Well, it's 1 over a smaller and smaller number. The fraction gets larger and larger. So that's something that L'Hopital's applies to. It's infinity over infinity. So then we apply L'Hopital's rule. So take the derivative of the top divided by the derivative of the bottom. So we're going to indicate with an H above the equal sign that we've applied L'Hopital's rule. So we have, again, the derivative of ln 10a is 1 over 10a times 10. So 1 over a. Derivative of 1 over a squared give us, right, negative 2 over a cubed. And it's the crucial thing in L'Hopital's that often gets overlooked. Before you reevaluate, after you apply L'Hopital's, before you reevaluate, what do you do?
Make sure it's still not still.
Yeah, so it is still in the form, right? This approaches infinity, the numerator is approaching infinity, rather the denominator is approaching infinity. So it doesn't help us much. We keep taking derivatives of this form, then we've got negative 1 over a squared up top, positive 6 over a to the 4th. Same scenario after same scenario. Yeah, you simplify. So every iteration of L'Hopital's rule, you simplify before you try to evaluate the limit again. So we're just going to simplify this, multiply by a cubed over negative 2. So that's the limit as a approaches 0 from the right. Negative, we have negative a squared, or sorry, a squared over negative 2, I guess. So we've L'Hopital, simplify, reevaluate. We reevaluate that limit as 0. Did sort it out? Why not? What, like, just remember to turn it into a quotient.
I mean, it's just weird going into the derivative process again there. Like, I wouldn't be able to do that. Like, after you take the limit of ln 10a,
Uh-huh.
I would never be able to take the derivative. I don't know why I have to do that.
Oh, so, well, we hadn't taken derivative at this point, we just rewrote it algebraically.
Yeah, no, I get that. I mean, like, your next step, like, how you guys got to the L'Hopital's part.
Yeah.
You're taking the derivative of the top and then y.
Because when we try to evaluate this limit, we get an infinity over infinity
So that tells you it takes the derivative.
of the top and bottom, yeah.
Separate.
Yeah, so L'Hopital's rule applies to any limit that evaluates to infinity over infinity or 0 over 0. Yeah, so that should be, at this point in your math, that should be your default. Is if you see a limit that's infinity over infinity or 0 over 0, it's always L'Hopital's rule. It's much easier than even limits that you can simplify algebraically. L'Hopital's rule is 99% of the time much more efficient. So our limit is of a squared ln 10a is 0 times a half, still 0. So I'll just summarize. So that's going back up into our original computation. That this limit also approaches 0.
What happened to the 1 over 400?
Nothing. still there. So that's a finite, a convergent integral. Why does it say it's defined there? It's weird. Looks like the computer's wrong. That's weird. Technology fails again. Okay, although we didn't address it here in the summary, if you look at item 3, we can integrate from negative infinity to infinity. We don't see any of those, but in order to do so, we just pick some value. They're calling C. And split that up into 2 different pieces, from negative infinity to C, and then from C to positive infinity. And then so from here, of course, we compute the limit as we approach C from the left, here as we approach C from the right. So what did they do? So yeah, A is negative infinity, and B is positive infinity. Yeah, okay, my bad. That's for a vertical asymptote. We don't have one of those here. And it really doesn't matter. It doesn't matter if the function's symmetric or not. You just pick some value in between negative infinity and infinity, and then compute that lower bound here, upper bound here. Again, we don't really see those, but you can do those in the same way. Has anyone taken probability classes? Like in probability, you can define things like even the mean of a probability function is defined as the integral from negative infinity to infinity. So those types of integrals are really common in probability, and you compute those this way. So again, we won't see any of those, but just worth mentioning in passing. Anyone have any questions on 8-9? Yeah. Sure.
So you use L'Hopital because you have a function that is a quotient that is the limit is no greater than the whole point of L'Hopital is to keep doing iterations until it's no longer in that form and it's going to get only.
Right. Yeah. That's it. Yeah. And L'Hopital's rule is based on. Do y'all remember the linear approximations? Like if I take I don't know, a really well-known linear approximation is for the sine function near 0. So if you take the sine function near 0, the sine function behaves or is approximate to the function x. Right, so if we looked at, and remember linear approximations is something that we build on in the next unit. But so here's the sine function. And what the linear approximation is the equation of the tangent line. So what is the equation of the tangent line of sine? at 0, it's just y equals to x. So the idea is instead of working with, I don't know, y1 as a function sine x, we can say is as long as I'm relatively close to the origin, sine x is pretty much just x. Right? So if I said, what's the sine of pi over 1,000? I'd say it's pretty much pi over 1,000. Right? So the idea of linear approximation is what, in a certain instance, is what gives L'Hopital's rule its justification, really. Because instead of looking at a function like f of x over g of x, and saying, well, I can't compute that limit as x approaches infinity, let's say, then as long as, or 0, let's say for this example, as long as I'm near 0, f of x behaves like its tangent line at that point, and g of x looks like its tangent line at that point. So derivatives are involved. It's f of a plus f prime of a. Right? So that's just the equation of the tangent line for f of x at a. And you get the same thing for the function g. It's the equation of the tangent line for g as long as we're near a 0. We are. And if we're near 0, then f of a and g of a are both 0, as the assumption implies. X minus a goes away, divides by x minus a, and you just end up with f prime over g prime. But it's based on the idea of the tangent line, or the linear approximation. And so later in the next unit, we actually look at, towards the end, we actually look at higher order approximations. Instead of approximating sine with its tangent line at 0, then we construct this polynomial that approximates sine for all values of x. Anyhow, chapter 9 deals with differential equations. We're only looking at 9.1 and 9.3, so it's just a very basic introduction to differential equations. The field of differential equations is vast. That's why you have a completely separate math class dedicated to differential equations. So we can't say enough about differential equations in 5-10 minutes or even 2 days. The author of your textbook says if you wanted to convince somebody that's skeptical of mathematics, the power of mathematics, then you would show them differential equations, just because the applications are so vast. In general, it's like if I don't know like an original quantity, like some sort of function that describes population growth, let's say, but what I've measured is how the population changes, then sometimes it's easier in some instances to describe how something changes versus what that thing actually is. And so if you can describe how it changes, then you can get back to what it is, right? So if I can describe like the function's derivative, then I can get back to the function, can I? Like if I know the derivative, to get back to the function, I use the antiderivative. So a lot, not all, I should say some, differential equations involve using the antiderivative to solve them, which is basically what we'll see in 9.3, a little bit in 9.1. The things in 9.1, though, you've seen those before, finding general solutions specifically and solving initial value problems. You saw that in Calc 1 when you said, here's an acceleration, what's the velocity function, what's the position function, right? So those were initial value problems. And then in 9.3, we look at separable differential equations. So just some terminology from our book here. So all a differential equation is, when you hear differential, what do you think? Derivative, right? Differential, derivative, same thing. So a derivative equation is just an equation that involves a derivative. So it's, instead of having like an unknown being, a number, the unknown in a differential equation is an actual function. And your goal with any differential equation is to figure out what the function is that satisfies those derivative equations. So, like one example, if I had y double prime plus 4y prime plus 4 equals to 7. Okay. So that's a differential equation. You're given that differential equation, and what you have to do is you have to find the function that satisfies that. Or f of x, f of t, whatever. Naturally, things that involve time, variable is usually t. But that's you know, a very basic differential equation. Any differential equation is essentially that. Here in an example, this example B, you have a second derivative plus 16 times the function itself equals 0. So what's the function that satisfies the second derivative of the function plus 16 times the function equals 0? And so that's what you're after. And so they actually solved that one for us. They say that cosine of 4x is a solution to this equation, to this differential equation. All right, so that's in a nutshell what a differential equation is. They take many forms, and many of them are difficult to solve, as you might imagine. I think once you get into Calc 3, then you'll start looking at partial derivatives in 3 dimensions. So really more applicable to like physics majors would be partial differential equations. We're looking at ordinary differential equations. Some terminology associated with differential equations is the order. I don't know, the bold didn't show up very well. The order of the differential equation is basically, it says the highest order, but it's the highest derivative that appears. So that equation, differential equation B, is a second order differential equation. A and C are both first order because you just have the first derivative showing up. The example we wrote down, second order differential equation. We're not going to really worry too much about if a differential equation is linear or nonlinear. We don't get that far into them. And then here a first order linear differential equation is defined, but again, it's linear, so don't really focus on that. So like we said, solving a first order differential equation where a y prime appears involves the antiderivative. So you've got y prime to get back to the function, you integrate. And we know when we integrate, we get that constant of integration, which gives us a family of antiderivatives. So those are like your general solutions to the differential equation. It's the most general you can get. So they call those general solutions. So those are the solutions that have like plus C in them or whatever. Initial conditions, I'm assuming everyone's familiar with that. Given an initial condition, you're able to find the constant of integration, right? So then we call those initial value problems. A solution to the first order initial value problem is the function that satisfies the differential equation. So we'll see a few exercises in 9.1. Say, here's a differential equation, and here's the proposed solution. Verify that this is actually a solution to that differential equation. So for instance, we're given that y of t is c e to the negative 5t. And what we want to verify is the following differential equation, y prime plus 5y equals to 0. So, I mean, this isn't really differential equations, it's more just calculus and algebra at this point. But in this way we can see how to actually tell if you have a solution to your differential equation. So we have a y prime, which means we need to compute y prime. So we have negative 5c e to the negative 5t as y prime. And then we're wondering that if we add 5 times the original function and add those two equations together, do we get 0? So 5 times y of t is just 5 times c e to the negative 5t. So, and we have to, those two things, just verifying the solution here. So y prime of t plus 5y of t is our negative 5c times e to the negative 5t plus this 5c e to the negative 5t. So clearly that's 0. And that means we've verified that solution to the differential equation. Any questions on that? Same thing in example 2. The function here is u of t. We're actually given both things, but I want to verify this. So our differential equation involves a second derivative. So we need to find the second derivative of u of t. So first derivative of u of t. Second derivative. So we want to verify then t squared times u double prime. So let's compute then t squared times u double prime. We have 20 times c1 t to the 5th plus 20 c2 t squared t to the negative 4 minus 6t cubed. So we've got our t squared u double prime, and we need to subtract 20 times the original function. So let's do that here. 20 times u of t, where u of t was given. So 20 times all of that, we have 20 c1 t to the 5th plus 20 c2 t to the negative 4 minus 20t cubed. Any questions on where we're at? Does that make sense, what we're doing?
Can you just go over the T-squared, you know, second?
Yeah, so then what we're doing is just multiplying our second derivative by t squared. So we're going to multiply this by t squared, t squared, t squared. All right, so we've got to verify that t squared u double prime minus 20u is equal to 14t cubed. So let's just subtract these. Put that result here instead of writing all of that stuff over again. So the left-hand side, we've got t squared u double prime minus 20 u of t equals to, we got 20 c1 t to the fifth minus 20 c1 t to the fifth, 20 c2 t to the negative 4 minus 20 c2 t to the negative 4. We got a minus 6t cubed plus 20t cubed. Just 14t cubed. So we have the fact that that differential equation is satisfied by the solution u of t, whatever it was, equals to that. Do y'all have any questions on either of those? Okay, we're also going to verify solutions to initial value problems. So very similar to what we just did, you've got a function given that differential equation and two initial conditions for y and y prime. So we want to verify the solution that y is actually the solution to y double prime plus 9y equals 0. But we also want to make sure that those initial conditions are accurate as well. So verify initial conditions. Y of 0 should equal negative 3. So y of 0 is negative 3 cosine of 3 and 0. The cosine of 0 is 1, which is negative 3. So y of 0 is indeed negative 3. And same thing for y prime. Y prime of 0 should be 0. So we'll just question that for the moment because we don't have y prime, but we can get y prime. Y of t is negative 3 cosine of t. So what is y prime? 9 sine of 3t. So it's 9 times the sine of 0, 0. Yeah. So the initial conditions are satisfied. Verified those. We'll verify the differential equation the same way we verified the previous ones. Easy enough? Can we move on? Or do we want to work that? Yeah, 9.1 is not too bad. I don't think 9.1 is anything outside of the realm that you haven't seen. So the general solutions to an equation like y prime equals to 12t to the 5th, etc. To find the general solutions, just use C1, C2, etc. for the arbitrary constants. So this is just an antiderivative problem. We would say y of t equals to the antiderivative of y prime. So we just take the antiderivative of 12t to the 5th minus 20t to the 4th plus 2 minus 6t to the negative 2 with respect to t. So, general solution then, we have 6, 12, 2, t to the 6th, minus 4t to the 5th, plus 2t, plus 6t to the negative 1, plus c. So that is the general solution, y of t, for that particular differential equation. Not bad, right? It's nice to, maybe nice to hit a section like this after everything we've been doing.
Now we do the general solution, just means the partial.
Yeah, antiderivative. It's a plus c instead of like minus 2 or something. That would be like a specific. So here you're given y double prime, so as you would expect, you have to do the antiderivative twice to get back to y. I'll just write it out. Okay, so antiderivative 1 gives us y prime. We have 15e to the 3t over 3. Cosine 4t minus cosine 4t over 4. So here, one antiderivative gives us a constant. Just, looking ahead, you could call that C, and if you get another constant, you could call it C1, C2, C3, whatever. I don't think there's a universally agreed upon way to label constants. You can call them A, B, C, D, E, F, G if you want. we're going to call them C1, C2, etc. So that's our y prime. It means y of t is equal to the antiderivative of y prime. So here you have 5/3 e to the 3t. What's the antiderivative of minus 1/4 cosine of 4t? Sine 4t times, what was it? Yeah, 1 over 16 plus C1 times t plus another constant. So that's the general solution. Now you get specific solutions when we start saying, you've got an initial condition, right? If you're given an initial condition, we're saying that this function has to pass through that particular point. So you might get, a family of curves, but with an initial condition, you say, this is my specific solution, right? Because it's the only curve that passes through that initial point that was given. Okay, questions on that? Yeah, more or less, yeah. So solving initial value problems, again, we've seen these in terms of the antiderivative to get y, and then we use the initial condition to figure out what the constant is. So let's see, we've got 2 of those. And then that's it for 9.1. It's worth reading the final note. If any of you ever plan on taking differential equations, something like this more than likely would come up for you. But it's sort of, what we're doing is sort of half the story. And so I just put that there. We're not going to elaborate on the uniqueness and existence proofs. But it is, I think, for many of you, probably worth at least knowing what's going on. So I think we'll look at these two in 9.3 on Tuesday, and 9.3 is pretty short as well, so we'll have time to review for our exam on Tuesday as well. Do y'all have any questions before we go? Yeah.
So it's 8 and 9.
Yes, right. Yeah, second exam covers chapter 8 and these 2 sections from chapter 9.
Alternate questions for example.
Yeah.